My name is Nate Emmer-Singer, and I wrote about how air sacs may have facilitated the growth of sauropods. The paper I chose to write about was Exquisite Air Sacs of Histological Traces in a Hyperpneumatized Nanoid Sauropod Dinosaur from South America. In this paper, researchers studied the bones of a Titanosaurus excavated in Brazil and discovered evidence of postcranial skeletal pneumaticity, or air sacs in their bones. These air sacs are created after birth and are the result of the respiratory system pushing air into the bones and hauling them out as they grow. As a result, these air sacs are connected to the respiratory system even after their child development. These air sacs are ubiquitous in modern-day birds. These researchers compared the fossils to that of modern birds in order to theorize how they may have been used by dinosaurs. These air sacs serve to reduce the weight of their bones while also aiding in their respiratory function. The bones mentioned in the article are located along the spine at the posterior dorsal vertebra. Their location is important to note because these are the spinal bones that are nearest to the organs, most notably the lungs, and wouldn't compromise their ability to support their large size like they would if they were located in their legs. This image shows the inside of a human bone and the inside of an eagle bone. Most vertebrates have bones similar to that human bone seen here. These bones are mostly solid with a bone marrow core. Avian birds, like the eagle bone shown here, are largely hollow. They do still have some bones that aren't and contain bone marrow, as it's used to create blood and therefore they need it, but most of their bones are hollow. It's obvious how lighter bones would help them fly, but the thing I want to focus on is their use in the respiratory system. Flying is very metabolically demanding. If your muscles aren't able to get enough oxygen, they will slow down and eventually fail. In the case of birds that have to fly for long periods of time, this would be fatal. The air sacs greatly increase the capacity and efficiency of their respiratory system. This image helps explain the process in 4 easy steps. The first is the initial intake of air. It gets moved past the lungs into the rear bones. Next is the first exhale, where the air is moved into the lungs. The third step is the second inhale, where waste air from the lungs is moved to the forward bones. Lastly, the second exhale pushes the air out of the body. The reason the system is so efficient is that multiple of these steps occur at the same time, which results in more consistent flow of oxygen as well as a greater volume being processed in total. In the case of these birds, both inhales and both exhales occur at the same time. Dinosaurs, as large as sauropods, likely needed these in order to support their titanic weight and size. Though their relatively sluggish movements wouldn't have seemed as taxing as birds, their immense size meant that they would have needed a more sophisticated respiratory system than that is seen in most vertebrates. The respiratory system we're familiar with, that being one built around a set of lungs, a heart, and arteries, is believed to have been a major part in facilitating the size of larger animals, including humans. These air sacs were possibly the next step in respiratory development to help support the size of titanic creatures like sauropods. These images are taken from the article and are 3D recreations of the bones that were analyzed. In the top 3, you will see areas marked as CC. These are smaller circumferential chambers. These are located at the end of the bones near the joints in between them. The areas marked CMR, are much larger circumferential chambers that make up most of the volume of the bone. These chambers would have stretched along a large segment of the spine and possibly the neck. Both kinds of bones were situated in a circular, radial pattern. It has long been a mystery how creatures this large were able to live. The 3 biggest concerns of such large creatures is how their bones were able to support their weight, which we're able just to see from looking at the fossils, how they can get enough food to fuel locomotion at that scale, and how are they able to move oxygen, nutrients, and waste throughout their body. Making this key step in understanding these air sacs, or a key step in explaining their physiology. The paper I chose was specifically about the remains of the Titanosaurus, but mentioned that a similar discovery was also made with Apatosaurus, which is another sauropod belonging to a completely different family. It's possible that these 2 species developed this trait independently, but it's much more likely that this trait was developed in early sauropods. It's possible this trait was a large contributing factor in their evolution that allowed them to grow into the hypergigantism that they've come to be known for. It was the significance of this discovery that made me choose this for my project. The top source is the article in question. The second source is where I found the image of the human and eagle bone, and the third image is the image, is the third link is where I got the image of the bird breathing.